Okay, now we're going to talk about gravitational field strength. So the gravitational field strength is the gravitational force exerted per unit mass on a small point mass. We have studied this in kinematics just as acceleration due to gravity, or free fall. All right? But if you think about Newton's second law, force per mass, that is acceleration, so that works out quite well. We use the symbol little g, all right? The formula that we get from Newton's second law, like I just described, is F sub g divided by little m, all right? The units are newtons per kilogram, or we also use meters per second squared. Use either of those. There we go. Let's say 4 in between here. There we go. And that's an awfully long thing to do. There we go. So we can sketch the gravitational field around the planet here. What I'm going to do, I'm actually going to do this on a new slide. I don't have enough space there. Make my little circle shape. Smart board, don't be dumb for me. Thank you. Good. Move around. All right. So the vectors here, all right, I'm going to draw them like this. And anytime you have any sort of field, whether it's gravitational or electric, the density of the lines will tell you the strength of the field. So what that means is that as you get closer to the surface of the Earth, there are more lines in a given area, right, than there are if you get further away from the Earth. You know what I mean by that? Well, I try to draw this all equally spaced here as it should be drawn. If I make a circle like right here, okay, I'll count more lines within that area than I will make that same size circle out here. All right. So that's the way we can tell any gravitational or electric field strength. Right. Magnetic fields are the same way actually. So yeah. All right. We'll come back here. So derive the expression, right, the gravitational field around the planet. So what I had before, little g is equal to F sub g divided by m. If we plug in Newton's law of universal gravitation, okay, I get big G times big M times little m over r squared. Divide that by little m, and little m's are going to cancel out, and you're left with just big G times big M divided by r squared. All right. So this is true, all right, for any point around the planet. Next one says derive the expression for the gravitational field at the surface of the planet, assuming all its mass is concentrated at the center. Again, this is just the same thing. All right. We're not going to be doing anything different, so I'm sorry, that's an old example. I shouldn't really include it anymore. Yeah. So that's kind of pointless there. Anyways, moving on. What is the resultant gravitational field strength at a point midway between the Earth and the Moon? So these add like vectors. All right. For what you're going to do here for part A, you're going to solve for little g, all right, based on the Earth. So big G times the mass of the Earth divided by half the Earth-Moon distance squared. And you're going to do the same thing. You're going to figure out little g, all right, for the Moon at that point. Mass of the Moon is what we're going to use here instead. And when you substitute in your numbers, what I end up with here, I'm not going to show all that right now. Spare you, you can plug them in on your own. This is equal to 0.11 meters per second squared. Very, very low. The next question asks, what is the resultant gravitational force? Well, F sub g, which is equal to g, to the m times g. That's going to be 1,500 kilograms times 11,000 meters per second squared. I end up with 16. So at that point, all right, you've got like a 1.65 kilogram object feeling the same gravitational force on the surface of the Earth as a 1,500 kilogram force would feel at that point. So, pretty cool. All right. Next, describe the variation in the net gravitational field between the Earth and the Sun. This is going to look exactly the same as what we had looked at before. Okay. The gravitational field due to the Sun is going to be much stronger as it gets close to the Earth. all right, it'll finally, dip towards the Earth, and the Earth will exert the greater influence. All right. It says determine the location when the net gravitational field is zero. In other words, that portion right there is part B. So when we do that, all right, what we're looking for is where the acceleration due to gravity from the sun is equal to the acceleration due to gravity from the Earth. That way it'll be completely balanced out. When you do that, okay, it's going to look like this. G times the mass of the sun divided by radius squared, distance between the Earth and the separation between the Earth and the sun squared. And here's G. And here we actually want to consider 1.5 times 10 to the 11th minus R, the whole thing squared. Okay, just like we did before with the moon example. All right, so the G's are going to cancel out here, and you can do some algebra, and when you do that, all right, I'm actually going to call this 1.5 times 10 to the 11th meters the Earth-Sun separation, all right? R is wherever we are in between them. I'm looking for that location which equals 0. Anyways, when you set this up, the equation that you end up with looks something, all right, like we basically have this 1.5 times 10 to the 11th minus R squared times the mass of the sun, right, is equal to R squared times the mass of the Earth. When you rearrange that whole thing, you can plug into your calculator and solve it. You can do the quadratic equation, both of which are kind of a pain in the ass. My recommendation is to plug in your calculator and solve. Alright, remember, set the whole thing equal to 0. You'll be able to combine these terms to the R squareds, right, which, you do that, you'll have a constant for this guy right here. You should end up with a radius. You end up with 2 answers, right? Remember, it's the same as before. One of those answers is bunk. This is the answer you want. So you see that this is very close to the Earth, relatively 80% of the way there, pretty much. Okay? Maybe a bit more than that. So that's how to do B. And what is the result of gravitational force acting on this probe at this location? Well, obviously, S of G equals M times G. G is equal to 0. That's where we were looking for this before. G. Sorry, the force of gravity is also equal